Hello and welcome to the latest web seminar by Big Instruments. My name is John Kowalski. I'm part of the marketing team here. Today's topic, dispersing and milling for energy storage. Our presenter is our dispersion manager, Mr. Andy Stumer. We are recording this, so if you would like to view it later, share it with colleagues. Immediately following the presentation, you will receive a link that you can forward. Also, due to the length of this presentation, we may be a little short on time for questions, but if you do have questions, you can either log them in the chat box or you can hit reply to any of those marketing messages, emails that you receive, and we'll get them to Andy or someone on his team. So with that, Andy, it's all yours, sir. Welcome.
Thank you, John. Thank you, and welcome everyone for joining us today. This call actually is doing this from Germany. I'm over here in meetings, and hopefully there is no connection issues, and we'll get through that presentation smoothly. So just go through a quick agenda. So we're going to talk a little bit about some modern energy storage applications, end-use markets, so on. Then we're going to go into the dispersion and milling process overview. We'll talk about the actual critical components that we need to watch for, the right parameters. And then we'll talk more about the actual equipment. So we'll dive into the type of laboratory scale. You can see that on that introductory slide, what we have, small scale, and then go into pilot and end up with some production equipment coverage for the electrolyte and separator slurries. And then we talk also about the lab capabilities that we have in Germany at VMA or in Big USA in Wallingford, Connecticut. And so you can see already we got a whole range of dispersers that are also fully functional media mills. So these particular models, they're called dispermats. They can handle many different applications, from the actual electrolyte development to the separated development. We can pre-disperse as well as mill, all with the same equipment from the lab scale pilot as well as manufacturing. And we also have a full range of horizontal media mills, which may be required for separated applications where we really need very small particle size and particle size distribution. We'll talk about those as well. So basically, the lithium-ion batteries, that market, as we know, is really growing a lot. I was in Florida 2 weeks ago at the battery show, and I was really amazed at all these startups that are coming into the market. We're offering new solutions, improved technologies, better range, and shorter charging times, just to name a few. Also, greener technologies. So it's really critical when we process these materials that we also select the right dispersion equipment and milling technology, as well as the additives that go into these slurries that help us make a more stable and improved product, and develop these next generation energy storage systems. So the solid state lithium batteries are really popular these days, and basically a lot of research has been done on how to improve these type of batteries, especially with the separators. So there is good technology out there that can really help you meet those goals. So we do offer a lot of different solutions, not only what you see in these presentations. Keep in mind that about 40% of all the products, dispersion equipment, milling equipment that VMA manufactures is actually customizable or for custom solutions. Being in Germany this week, I can tell you I've seen some really interesting new developments with respect to this renewable energy market and battery development applications, systems with 3 shafts, for example, with the ability to do everything in a nitrogen environment with special feeding ports. So a lot of these products can be customized and made specifically for your application. So as you can see, the market is really growing exponentially. There's a lot of opportunity in the development process and also on the equipment side to really select and then choose the right type of equipment that works best for your development process. We're putting a lot of research into that arena, and you'll see right here on the next slide after this one, where we actually introduce a whole new line of Dispermat specifically for that battery market. So the equipment is used, to disperse and mill a lot of different products that go into these slurries. Silicons, electrodes, silicon oxides, lithium, polymers, different type of ceramics for these separators, as well as the carbon graphites, nanotubes, and carbon blacks are among the most important ones. There's definitely more, but these already been used. Our equipment's been used successfully in dispersing these materials into these slurries. So the the lithium-ion battery development is basically you have these electrolytes, and don't want to get into too much detail. You're probably very familiar with, but it's basically the substance that allows these ions to flow freely between the anode and cathode. And these electrolytes might either be fluids or solids based with different soluble salts, acids, that can act as these electrolytes that we will be mixing and dispersing with our equipment, as well as these separators, these coatings that we will also have to mill really fine to get a really small and fine particle size distribution to improve the transfer efficiency of these particles moving between the anode and the cathode. So the right equipment is key to basically improve the slurry performance. And also it's very critical that we measure or look at the rheology and viscosity of our slurries as we develop them. That will help us also with the downstream and upstream processing. So for that purpose, we have developed some new key technologies that help us get a better understanding of what the actual viscosity is during actually our dispersing process. So with that, I want to share with you that's the new Dispermat line for the renewable energy market. It's called Dispermat AERE, VLRE, with the torque measurement system. So the VL is actually a vacuum dissolver. You can see that on this picture right here. And we actually included a specific torque measurement sensor that measures the exact torque on the shaft separately, not from the frequency inverter like it's usually done, which is not as precise. So we can get a really accurate reading of our torque, which is an indirect measurement of our viscosity in real time during the actual dispersing or milling process. So we have a really tight accuracy of 0.1 on the torque. With this particular machine, we use what's called the C technology control panel that allows us also to monitor these viscosity shifts during the dispersion process in real time. You can record that data, send it over to a computer, as well as all these other critical elements such as dispersing speed, energy input, torque value, obviously, but also the actual tape speed, RPMs, time, as well as temperature, are all recorded. And then we'll be able to look at that in a graphical interface to see a trend line for each of these values, that we can actually see exactly what's happening during the dispersing or milling process, where our viscosity is going out of range, increasing or decreasing based on the torque measurement. This particular TMS sensor is really good repeatability and reproducibility. It's something that's really new and has really helped quite a good number of customers really get a good handle on the change of viscosity during the actual dispersing process. And we do this again with a special sensor, not actually down from the frequency inverter. So it's a really good tool to develop your process and then upscale it to pilot or manufacturing, where we also have the same technology that you can add on to that type of equipment. So here is just an example of a cathode processing scenario where we have carbon black and we add some other raw materials. We use the Dispermet VL with the vacuum capability, and then basically are able to really disperse that material. We have the ability to also, if some customers like to do that in a more dry environment, we have the ability to add a port for inert gas, so we can use that in lieu of other materials. That's the option there. Argon gas or nitrogen. Some customers prefer to have a nitrogen blanket, so we can create that with that particular machine. Here's an example of a cathode slurry development using a CN20. It's a Dispermet that is not vacuum. That's a standard disperser that we offer. What we did here is we first pre-dispersed with the CN20 with just a standard impeller blade for about 1 hour. We started at roughly about 100 microns of particle size. And then we were able to reduce the particle size down to about 30 microns in 1 hour. And then what we did is we swapped out the dispersion impeller, that shaft, and we replaced it with the TML basket mill, which basically gives us additional shear and really allows us to use the media inside the basket mill with that milling disc to further de-agglomerate and reduce the particle size down to about 2 microns, and we were able to accomplish that in about 3 hours. We're able to actually go down much smaller if that's required with the TML basket mill. We have the ability to go down to around 500 nanometers. If customers would need to go smaller, then we have the ability to do that with the nano kit, or alternatively move over to a horizontal medium mill. But the great story here is that we did both the pre-dispersing as well as the milling on one piece of equipment. So that also saves time. You don't have to switch in between the pieces of equipment really, and also desk space or bench space. You only buy one disperser with that TML basket mill attachment to allow you to do that all on one piece of equipment. So basically, just give you a little bit of an overview of what's actually happening during the dispersion process. So we're trying to basically wet these solid particles as we're introducing them, for example, the carbon black, and then we try to break down these agglomerates, which are these larger clusters of particles. They are bound together by these invisible forces called Van der Waals forces, these invisible magnetic forces that basically cause these particles to stick together. We try to break them up, and then they become smaller particle clusters. We call them aggregates. And these clusters, we'll be able to get there from the agglomerates to the aggregate level by using a standard disperser with the cow's blade or impeller blade. And then if we want to go from the aggregate level down to the primary particle level, we need to do that during a milling process. That's the only way we can introduce enough shear force to really break up these binding forces at the aggregate level to be able to get down to the primary particle level. And then it's obviously important, we want to stabilize this particle in our slurry, so we need to also use the right additives that our sister company, Big Additives, offers to really keep these particles in a suspended state where they should remain. So this slide, I think, is really nice. It shows you kind of the process. So first, again, you start with the standard blade to really bring down the larger particles, break up these binding forces. We also wetting during that process. And then once we're about roughly around 20 to 30 microns, that's when we would start the media milling process. So for that, we either can look at the basket mill, as I had shown you earlier in the slide, or a horizontal bead mill, or actually vertical bead mills, which we'll also cover a little bit later. And then again, we need to stabilize these particles once they've been separated with the different type of additives that are available on the market today. So here, basically, we developed, this was a development with the new Dispermet for fuel cell. We used the AE, and basically we did both the anode and cathode dispersing, as well as used it then for the ceramic separator coating. We used the TML basket mill. In this case, for the actual ceramic separators, we needed to use the SL mill, which is a horizontal medium mill, because the particle size was below 500 nanometers, more like in the range of sub 100 nanometers. So the basket mill no longer was sufficient to really bring down the particle size below 500 nanometers efficiently. So we were able to do that with the horizontal medium mill. But for most applications on the electrolyte, for electrolytes, the basket mills are doing an excellent job to get us down to where we need to go in terms of particle size, as well as particle size distribution. Big USA has a variety of additives that go into these formulations to improve the wetting as well as dispersing. In fact, they also have a variety of defoamers. If you want to use that, or you could use the vacuum that also pulls out the air really nicely if you want to keep that out of your formulation. And one of the chemicals or the additives is the leponite RD. And basically, that's an additive that they sell for various types of formulations. If you're interested in finding out more about the additives, we can put you in touch with our colleagues. Erin Kelly at Big USA is a resident expert for the renewable energy end-use market, and she has a lot of knowledge on selecting the right type of additive for your specific application. So on this slide, basically, what we show is at what point you should really move over from a dissolver to a milling process. So again, for the beginning of our process, we always use the dissolver with the cow's blade to really deagglomerate these larger particles. And then when we reach between 10 to 20 to 30 microns, it depends on the formulation. So that's just kind of the rule of thumb, where we then need to move over to a medium mill if we want to go below 10 microns. In most cases, we try to do that already when we reach 20 microns or 30. That's when we already start using bead mills, because they become a lot more efficient and you get down there a lot quicker than if you start staying with the dissolver for extended periods of time. It just needs a lot more time to deagglomerate because you're just not able to get as much shear force into your slurry to break up these binding forces. It's a lot more efficient at that point, to move over to a bead mill. So for pre-dispersion, what's really important there with the blade is we have to look at the right tip speed. So it's not only about the RPMs, it's always the relationship RPM to the diameter of my blade. What we're looking there for is the tip speed between 18 to 25 meters per second. That's ideal. We use different types of dissolvers. We have the SC for manufacturing, LCCV, CN and AE for that, as well as that new renewable energy unit that I showed you earlier. That's part of the AE series. And then for fine dispersing or milling, our tape speed is slower, between 10 to 16 meters per second. So not quite as quick as when we just use the cowl's blade. When we use the media with the milling disc, we go down in tape speed, and we're going to be very efficient. No need to go higher than that. So for that purpose, we have the vertical bead mills. We'll cover that. It's like a pot mill that goes right onto a dissolver. It's the advantage of having that modularity of our disper mat. So it's just an attachment, or the basket mill, which we discussed already, which would be another form of attachment, or a different system altogether would be the horizontal media mills, where we have a whole range for production, pilot, as well as lab scale. So very important in the pre-dispersion process when you're developing your slurries is always select the right blade diameter to your vessel. It should be about 1/3 ideally. And basically you have the option to go and increase the blade diameter depending on the viscosity of the slurry. So the table on the right kind of shows you what range you have to move, to larger blades or smaller blades depending on the container size. So there's not one blade that fits, just one container. So you really have a range that you can use to dial in the proper blade diameter for your different applications. And obviously, one other thing, it's important when we are pre-dispersing to remember that we are putting in energy into our slurry. So usually the pre-dispersing time can be up to about 1 hour for particular materials. Usually it's faster, but since we're putting in energy, it's important that we remember to also cool our slurry. So for that reason, we recommend that you use double wall containers, jacketed containers, that basically allow you to then control the temperature. Our disper mats, the higher end models, all have temperature readout capabilities. So they always tell you what is the temperature during the dispersing or milling process. And you're able to actually program, which is really important, cutout values that basically are cutoff values that basically allow you to monitor not only temperature, but also tell the machine to reduce the energy input or run at a different speed once you reach a certain temperature threshold. That's really critical, or shut down the equipment automatically once it reaches a certain critical temperature point. The other really critical part, what we discussed earlier, is always the tape speed. So basically, tape speed is always calculated the RPMs, times the diameter of your dispersing blade, times pi. If you want to calculate meters per second, then you would divide everything by 60, but you would calculate the dispersing blade in meters. So if it's, let's say, 50 millimeter blade, you would use 0.05 and times pi, times the RPMs, divide by 60. That would get you to the meters per second that would be indicated on the disper mat, on the C control panel. The donut effect is something that's also really critical. It's important. It's a visual cue. It's really called that. It's something that we see when we actually look inside of our slurry. You can see right here, there is a really nice donut. Looks like a donut that's formed when we optimize our actual tape speed and blade diameter to the actual container size. And you should see that if you have really low viscosities, sometimes the donut doesn't form because it would collapse immediately at the moment it's formed. So the ideal range to see a donut would be probably anywhere between 1,000 to 5,000 centipoise, or in some cases even higher, depending on the blade diameter. But that's usually the sweet spot in that range. that you should be able to see the donut. So actually what's happening here is, as you can see, the shearing is taking place at the edge of our blade, where we have these teeth, not only on top, but also actually on the bottom. It's not shown here on this slide, but there is also a lot of shearing that's done underneath the blade in the same area. So that's where actually all these binding forces are broken up, and the particle size is being reduced. So in this case, it's just it's a good picture of an optimized dissolver prep. We have about 21 meters per second of tip speed, which is optimum, and we're putting in about 850 watts of energy. So this really looks good. That's what you want to see when you look inside of your pot during the pre-dispersion process, and everything at this point is optimized. Now we have scenarios where it doesn't look quite that way. So in this case, we have the same tip speed, but we're only putting in 320 watts of energy, and we're not able to really get a donut. So the way that you change this is by changing the diameter of your dispersing blade, and then you would increase the energy that you're putting in, basically putting you back into that optimum range of tip speed of the donut window. And in this case, we're putting in a lot of energy, 900 watts, 20 millimeters per second, and we have no donut effect. Again, that can be changed, either formulation related, change basically, the additives that you're putting in, or the base formulation, or again, you would change the blade diameter to get the donut. So it's really critical that we always watch how long we pre-disperse. So it's take samples during the pre-dispersion process and see how far am I coming down with my particle size. So a Hegman gauge is really good for that application. And then the donut effect, again, tip speed between 18 to 25 meters per second. Blade diameter, also the blade type. Some people have custom blades that work well for their applications. Also the right blade type, depending on the viscosity I'm running, so I'm able to put in the right amount of energy. The volume of mill base, we recommend anywhere between usually about 50% of the container size, but you can go up to about 70% or as low as 40%. But you shouldn't go lower or more, otherwise you're spilling. If you go too low, then you're not able to properly oscillate the blade, and it's not ideal either. So ideally, you should stay within the 50% range. Also, if you're milling after the pre-dispersion with the basket mill, you don't want to have too much product in the container, or that weight of the basket mill would cause the product to just spill as soon as you apply any type of shear force and increase the tip speed. The filler concentration of our raw materials that we're putting in, we're trying to keep the temperature as low as possible. Better for the product usually, and for that we control the temperature with the chiller, with the containers that are jacketed, and also the PT100 probe that we have that basically measures in real time, and then you get the readout on the control panel of the Dispermet, where you can then program these cutoff values we talked about earlier, and also warnings. Let's say you have, 70 C limit, then you could program the unit to give you a warning at 60 C and the warning at 65, and then either reduce the energy input once it reaches 70, or turn off the machine automatically, or just reduce the tip speed. That's also an option. And then again, the additives play a role to keep these particles in a suspended state, and you don't have any flocculation once you complete your batch. So once we complete that process, if we need to reduce our particle size further, that's when we really need to use the milling technology. Um, so there for the dissolvers, the blade can only do so much, therefore giving us only a limited amount of energy that we can put into our mill base. Shear force obviously is limited as a result. It's only there to deagglomerate, not to go down to the primary particle size. For that, we need to do the milling. And it is a critical step for any dispersion. It's not recommended that you go straight to a media mill when you have very large particles, because that would mean that it could clog your screen inside of the mill. If you're using horizontal mill, it could clog your dynamic gap, and you don't have good flow of your material. So it's really important that we first reduce our particle size to a manageable size and then move over to a media mill. We would then go down to the primary particle size. Bead mills, obviously, a lot more energy can be put in. We're able to then go down to from the aggregate level down to the primary particle level, improving a lot of the product characteristics that may be important in your application. So inside of a bead mill, what's happening is basically use media, we use beads, and there is a milling disc or a rotor, and as the rotor turns, the media, the beads. Usually, we recommend that ceramic, either yttrium or cerium stabilized. They're very hard, and these beads then basically get thrown around in your slurry, and that action is causing these particles to really shear, not at the point of impact, but before at the point of impact, these particles actually get pushed away. So it's very unlikely that we are crushing the actual particles. It's that that shearing is caused by the media really drifting towards each other at high velocities, and that's what's kind of causing these particles, these bonding forces to break up and make the particles smaller. It's like the example is if you're like inside of a bathtub as a kid and you try to catch the rubber duck with both of your hands, and as you push your hands together, it's difficult to get the rubber duck. You're pushing it away. That's kind of the same principle of what happens in a media mill, except at much higher velocities and speeds, and a lot more hands, in this case media, that trying to basically push these particles away, causing them to shear. That's really what's happening inside of a bead mill. So kinetic energy, here's a formula. If you want to write it down, I will share this presentation. It's really important to have, a high amount of kinetic energy to really break up these binding forces. Therefore, we recommend that you use a higher quality bead, ceramic, a lot heavier than glass, for example, or other materials that don't give you that high kinetic energy based on the weight that you will get with a ceramic bead. So here's a good slide. You can see, for example, glass, 2.5 specific weight versus 6.1 is cerium stabilized, and the hardness also on a cerium stabilized ceramic bead is a lot harder than glass. So we always recommend use really high quality beads. They should ideally be perfectly spherical and not some ragged particle or oval shaped bead that we all sometimes have seen on the market. Beads can get expensive, but we believe you get what you pay for. And usually the very low cost beads, even though sometimes you get them, in ceramic, if you look at them closely on the microscope, they might not all be perfectly spherical. So you really want to go and look at that, where you're getting your beads from, and the quality there is really important. And again, always go with the heaviest bead you can find that's not contaminating your slurry. Obviously, metal beads are not suitable for the application. Therefore, ceramic is ideal and has a really high hardness to get the job done. Stay away from glass. The bad news, they're cheap, but they shard, and then basically break up. You have shards in your slurry, and then you can filter that out. It's not a good thing. So again, here you can see what's happening. So you have these beads drifting together, and then right in between that midpoint, that's where actually the shear forces cause these particles to break up, and then basically turn them into the smaller particles, ideally primary particle size. If you have enough milling cycles, you should be able to get down there. So these are some of the key parameters that we need to watch out for. So again, particle size after our pre-dispersion with the blade. Uh, the lowest point, about 10 microns. At that point, we do have to mill. We can be anywhere between 20, 30 microns. We can already start to medium mill. Again, bead size, really critical for the kinetic energy. Specific weight of the beads, the volume of beads. So depending on what type of milling process, whether you use a pop mill or a basket mill or a horizontal media mill, there is different range of bead volume that you can put in. Usually it depends on the manufacturer and also on the design of the mill. But that's something that is shared by obviously us and the manufacturer, depending on the milling chamber volume and rotor type and so on. Again, shape of the beads, always try to get them perfectly spherical. The milling disc speed slower than the tip speed when we pre-disperse with the blade. The milling disc should be anywhere between 10 to 16 meters per second. It's really important. You don't go higher, you're not going to get a faster milling time. Product temperature, really important when we're milling. We're going to put in a lot more energy than when we pre-disperse. So that is critical, that we not only cool the actual container with the jacketed vessel, but that we, in instance of a basket mill, that we also cool the actual basket when we're doing the milling process. So we need to cool both, or the milling chamber on a horizontal media mill, that we get cooling all around during the process of milling, as well as the vessel that holds our product. The number of passes, how often does it cycle through our media mill? It's different on a horizontal mill than on a basket mill, but cycles matter. And the more we cycle our slurry through our media mill, the better, and the more, the smaller our particle size will get. Milling time, the longer we mill, usually the smaller the particle size and the better the particle size distribution. When we use a horizontal media mill, how long does my slurry actually stay inside of my milling chamber? So if we increase the rotor speed or pump speed, that means we cycle faster, cycle more. Or if we're slower, it stays in there longer and it should cycle slower. So that depends on the type of formulation you have. There is not one number that applies to every formula. That's something that we would really need to see specifically for your application and dial it in. So we have a lab space up in Connecticut or here in Germany where we can do trials free of charge to actually help you dial in these critical parameters. Viscosity of the mill base, very important when we're milling. So if our viscosity is too low, it's more difficult to put in energy. So we want to optimize the viscosity. If the viscosity is too high, then we will have a problem cycling our mill base through the basket and get it out of the screen and back around. So the material always has to be flowable. As well as when we use a horizontal media mill, we should always have a flowable product. We had applications where the viscosity was so high that the material didn't flow anymore. In these cases, we couldn't use a basket mill. We have to use a horizontal media mill with a plunger type setup where we're actually forcing the material through the milling chamber, and then hopefully it comes back around. But optimizing the mill base to a reasonable viscosity where we have a flowing product is really critical when we are milling our material. And then obviously the types of bead mills we talked about, pot mill, vertical bead mill, or the basket mill or horizontal media mill. And we'll cover that in more detail. So one of the key takeaways is really the advantage with the Dispermat. It's an excellent solution to develop your slurries or coatings. So we can attach all these different elements onto one piece of equipment. So it's very versatile. We could use a rotor stator. We actually recently had an application for battery coating where we were able to really get down the particle size to a really reasonable level just by using a rotor stator. We didn't have to actually mill. So that was really nice to see that we were able to do that also on the same piece of equipment where we usually do the dispersing with. On the bottom left, you can see that APS system, which is that vertical media mill or pop mill that we can attach. It's more for the laboratory scale. It's not really for manufacturing because you would need a tremendous amount of beads in this type of setup where you can have 100% bead loading to your product loading. So it's more for lab scale and not for manufacturing. But the way this system works is you have a container on top and the container on the bottom. On the top, in the top container, you have your slurry. You can pre-disperse in here with the cow's blade. When you reach the right particle size, then you swap out the blade and you change that to a milling disc, and you put your media, the beads, into the container on top. You close it up with that lid, and then you are running that just as a regular media mill, depending on how small you want to go. When you're completed with the milling cycle, you can hook up an air hose. There's a socket on top of the cover of the lid, and purge your material out from the top container to the bottom container. You remove the drain plug that's in between, and then you basically can purge your slurry efficiently into this container right below. The beads will stay in the top container because there's a screen separating the top and the bottom container, as well as the drain plug. And that's an easy way of milling for lab scale applications, not really for manufacturing. We have a vacuum system that's an attachment. Some people like to disperse or mill under vacuum. And then we have the standard basket mill system on the bottom right. That's really good for us. It's very scalable, very efficient. We have a lot of customers in the battery world that use that piece of equipment very efficiently and get really good, nice, small particle size, as well as particle size distribution. With the TML, we can go down to about 500 nanometers. With the nanocade, a little bit smaller, but that's good for most of the application. If we need to go smaller, we would then use a horizontal media mill. We also have the option to add a wall scraping system for really thick slurries. Sometimes customers like to get everything off the container wall, so that's another option, that ASC system that will help us do that. So this is again a picture, a close-up of that new renewable energy lab scale battery slurry disperser. Which the torque measurement sensor we covered earlier is a really good feature, giving us this indirect measurement of our viscosity in real time. We have the ability to turn it also into a vacuum system. We can add a purging valve for nitrogen or argon gas if customers want to be in a dry environment. We have obviously variable speed. We can also run this unit with what's called constant power or constant speed. Instead of just selecting a certain speed, you can select a certain amount of energy you're putting into your mill base, and then the blade speed will change depending on the change of our viscosity. So that's really nice. The maximum RPM on that lab scale unit are 20,000. It's pretty high. We're able to achieve that really quietly with our awesome technology, brushless direct drive motor. Uh, these are super quiet. If you ever worked on a Dispermat, nothing like it on the market. You can hardly hear them when they're running. They are um, super easy to run. Also, very low vibration. That's another key feature. It's a really nice technology. They don't break. We have customers that use the same motor technology for over 30 years, and the only thing that we had to replace was basically the control panel that gets worn out over time from dust and dirt. But the motors themselves will last a lifetime. I've been with the company for 17 years, and I can vouch that I've never seen a broken motor. The only thing that goes bad is usually the control panel over time. We also offer these models in an explosion-proof version for some applications where customers require that. We offer that also for our large-scale manufacturing units. We have the software available that allows you to basically store all the data. You can program recipes, um, store them by batch name or product ID, and then port everything over to a computer and store it on there, or you just put it into an Excel file, and then you can create lab reports, share that with your team, and then also watch the entire dispersing or milling process in real time in a graphical interface where you would then be able to see trend lines for each of these variables that we discussed: your time, temperature, torque, tip speed, viscosity, in a graphical interface, where you see then change in the dispersion process very easily. Again, direct drive, no belts, no wear really on the motor. Again, super quiet and no vibration or hardly any vibration. A lot of safety features also. Just want to mention all these units are intrinsically safe. We have a number of safety features built in. The container clamping system. So basically that wheel on the right side there, that allows you to tighten the container. If the container is not perfectly centered or loose, then the machine will indicate that on the display. It will not start up unless the container is fully secured. We also have what we call the working area threshold setting, H1, H2. So we have an upper and a lower limit inside of our container. And that between those two ranges, the H1 and H2, we can operate the disperser or the media mill. If someone were to lift up or push the up button, then the disperser will automatically stop at that point, so that there is no moving parts or blade outside of our container to throw product around the lab or injure somebody at these high speeds. So these are just two very key safety features that are a part of all of our units, and ensure that everybody is safe when they operate within these parameters. So this here is an example of the Dispermat VL for the renewable energy market, fuel cell market. We have an optional wall scraper. Some people prefer, that the slurry gets completely mixed and there is no residue sitting on the container wall. It's basically all sealed up, so we can draw a vacuum. We have the ability to also add ports, again, argon gas and nitrogen, to that all in an inert environment. Different container sizes. This is just one example. We can go as small as 1 liter up to 50 liters or higher for production purposes. So really nice unit with different options. Then we also have customers that don't require all these fancy features. They just go and say, hey, I just need something really simple for my lab. I like that direct drive motor technology. These units are super quiet. We want those, and therefore we also have the low cost, the economy line battery model. So basically, this is just a simple dissolver. Again, you have the modularity. You can attach a basket mill or a bead mill onto the same machine, and these are for smaller volumes. The display will not give you a lot, only the speed and the timer function on the LC. So it's pretty straightforward, small scale disperser. Again, 20,000 RPMs for really high speeds, as well as high tip speed that is needed to really get a slurry prepared properly. The next model up is the CV line. I can share with you, we're introducing a whole new CV later this year. It's an awesome looking machine. The CV is perfect for small product volumes. We also integrated a scale on the new model that basically allows you to weigh your material next to the disperser and then have the all the information from the scale displayed on the control panel. It will no longer have that box that you see right here. It'll have a separate control panel like you've seen on the other model, and you'll be able to have all the safety features integrated as well. So really, really nice looking machine. Again, same motor technology. You'll see speed, torque, product temperature, timer. Actually, also the new model will show you the actual tape speed also. So this is going to be the most advanced lab scale disperser / medium mill on the market, allowing you to do up to about 7 liters of electrolyte or slurry development. Then we have the CN, which also will have a facelift later this year. Same principle, new control panel, also something that's really scalable. So we have these for small volume lab space, but then we can go up to really large, up to about 150 liters, which is already pilot scale within the same product family. So very versatile piece of equipment. Again, the full modularity to giving you all the flexibility you need to do the dispersing and milling all in one piece of equipment. Same model for pilot, same features, just larger containers. Again, jacketed containers are available in many different sizes. We also have jacketed vessels with the ceramic liner, if that's what's required. We have also in the AE series right there, we have the explosion-proof models available. That control panel is that new control panel that we talked about earlier, and that will also be on our new CV3 series, and the CN will have the same control panel, in addition to that facelift that I talked about. And then again, for pilot, we also have the AE series up to 100 liters on the AE. So we have also a variety of horizontal medium mills. We got the SL mill for labs applications, and then we got the RS for manufacturing scale. Excellent horizontal mills. We have also a nano kit if somebody wants to go below 100 nanometers. We have ceramic lined milling chambers, either silicon carbide or zirconium, white ceramic. Also the rotors can be fabricated with different ceramic materials depending on the application. Again, fully jacketed, not only the supply vessel, but also the actual milling chamber. So here is your supply vessel. There is a motor with a disperser blade and a pump that will actually mix your slurry and then push it into the actual milling chamber right here, and then circulate the product back into the supply vessel. So you have a really smooth circulation in and out of our medium mill to ensure efficient grinding. We have one of these models in Wallingford, Connecticut. So if you ever want to come up and join us, we'll be glad to share show that to you and run your slurries on it. For the manufacturing scale, different sizes, we can make them even larger, up to 1,000 liters per hour. Again, NanoKit is available, vacuum option, explosion-proof models. So depending, really, we can customize that specifically for your application. Quickly, manufacturing scale, disperser, just what you saw on the small lab scale and pilot. Again, fully modular with the quick change system, allowing you to also mill and disperse on one piece of equipment, add a vacuum upgrade with these different nitrogen or argon ports, wall scraper optional, as well as explosion proof. We can go up to about 2,000 liters of product with our largest manufacturing scale unit. Here's just a quick slide showing you that quick change system. So we actually able to go very quickly from a dissolver over to a medium mill, back and forth, all on the same machine. Again, ceramic option. We can also add a rotor stator on the same piece of equipment with the same quick change print system with that principle. So that means you buy one piece of equipment to do both, your pre-dispersing as well as your milling. So that saves you space. You buy one machine, money for maintenance and so on. It's a super cool concept, and a lot of customers really like it. They see here with that cart, that's what's used to basically do that transfer from a dissolver over to the mill head. We just put the cart in there, lower the shaft, that motor flange on top, loosen the clamping ring, turn the assembly 180 degrees, and then you're just moving on to your milling. That change takes about 5 minutes, 6 minutes. We did it this morning on a customer trial. So it's really efficient. Here's an example for a production scale with vacuum. We also have nitrogen purge on this particular model. We can improve our homogenization, obviously pull out all the air, have faster product transfer. We can eliminate all the foam, so there's no need for a defoamer. We're putting a lot of energy by running under a vacuum, or again, we can do that with inert gas as an option. And we are actually constructing a piece of equipment right now. I can tell you that has 3 shafts. It's extremely capable for a very unique application, and so there is a lot of customizability and design that we can work with depending on your requirements. This system is interesting. It's for manufacturing. It's already an integrated mill head, so you don't have to swap out anything. So it's a disperser plus the medium mill all in one. So you first pre-disperse, and when you're ready to mill, you push a button and the mill head comes down, and now you're milling. It's called the TM, 2-in-1. It's a very, very cool system, I would say, because it's extremely efficient. You don't have to push containers around. Everything can be done from start to finish on one piece of equipment in one location. Here is another slide just showing you some of the movement of the actual basket. So first you pre-disperse, you push a button on the control panel, and then the basket comes down, and now you have a full-fledged milling system. Again, perfect cooling with our basket mill. Not only the container, but also the basket itself is double-walled for really good cooling efficiency. That's so critical when we're milling. Here's an example of a real live TM, 2 of them. The blades have not been installed. They're behind the gentleman right there on the left. You can see them leaning against the blue drum. That's on the bottom of the shaft. That's where we would install the blade, and the basket's already up there. So on the right side, that's basically what it would look like during the milling process. Once the container cover once everything is closed and you're actually milling. Picture of our basket mill. So that screw right there is where we actually put the media. We have a cow's blade on the bottom to draw the media, the mill base out of our basket and then pump it back around to the top. Again, extremely efficient, very easy to clean, not like a horizontal mill, no wear, no O-rings, no seals. They're super efficient and very effective. Um, Here's just the makeup of the basket mill. So we have our entry on top. In order for the mill base to get sucked into the basket, we have a patented steering and pumping wheel that creates a vortex. That chamber gets filled with the media, with the beads. That milling disc right below the pumping wheel will take care of the milling. And then right below that, we have a screen where we can actually force the mill base out of the basket with the help of that cow's blade and then pump it back around to the top. So we have a very effective movement of our slurry in and out of our basket mill. Again, you can see these cooling lines. So we're cooling the entire basket for optimum cooling efficiency and temperature control. And this graph, you kind of can see how the product moves effectively in the container and in and out of the basket mill. That's a slide for the APS, what I explained earlier, that pop mill with that 2-container system for the lab space. So with, again, 2 containers, top container has our mill base. We add beads, we mill. When we're done, we purge it with air. We hook up an air hose and purge it. And then the mill base gets drained or pushed out into the container on the bottom after we remove the drain plug. Again, different mill heads, ceramic. We also have ceramic lined milling chambers for the battery slurry development, which is critical that we don't have any wear off our stainless steel into our slurry. Different control panel options. So that on the left, you can see that C control panel, giving you the indication of control capability, RPM, energy input, torque, tape speed, temperature, as well as the timer function. We also have, with the torque measurement system, the ability to measure that viscosity in real time. We can program this depending on our, badge type, badge name, and then basically we're able to just recall that all these settings and it'll replicate it exactly the same way. Also really good if we want to go from lab to manufacturing. It's very scalable. On the right side, you see very traditional, simple manufacturing type control panel. And here is a picture of our lab in Germany at VMA. That's where we build all the machines, as well as testing facility. We have a same type of lab in Connecticut where we have different types of dispersers. We have the new AE technology, as well as the horizontal SL with all the different mill heads, also different basket mills and rotor stator attachments, as well as vacuum attachments in our lab. One thing I want to point out, we have a lot of good collaboration with our sister company, Big Additives. They're the experts in these raw materials that go into the slurry. And in conjunction with them, if you ever come and visit our facility, we can include our folks from the additive side to really help you optimize your formula, give you recommendation on type of additive that would help you, and then use our equipment to really process the material. So the lab is in Connecticut. It's a first-class lab facility. We call it the Battery Additive Development Center. We really do a lot of work up there for the renewable energies market. We're not only able to do trials for you or with you, we'll also basically help you to scale up your products to manufacturing. If you're interested in large equipment, again, we can use the resources that are available from the Big Additives team to help us optimize the formulas and make them process better and easier and get to the desired results. You can only also come in just to look at the equipment without running any materials. We'll be glad to show you the setup and how these machines actually work and function with these different attachments, or come up just if you want to learn more about milling and dispersing in the real world. We can also set that up for you to get trained better or have a seminar for you. So that covers it for today. Hope you enjoyed the presentation, and thank you very much.
Very nice. Thank you, Andy. Always appreciated. I know you're overseas and it's been a long day for you, so we appreciate your time. Thank you for everyone attending. You will receive this recording link immediately following this presentation. So take a look at that, save it, grab a couple of those screenshots on the formulas that Andy mentioned, and feel free to share it with colleagues. So with that, have a great day and a great rest of your day. And we look forward to seeing you on future BIC Instrument webinars. So thank you. Bye-bye.